Hello, everybody. Thank you for joining us today. My name is Topher Buck. I am the IC2 project manager here at NUMOA. I think we will probably wait an additional minute or two just to let people join us, but we will get started with this webinar very quickly here. So please hang on and we'll be right back. All right, well, I think we'll go ahead and get started. We've got a lot of material, really interesting material to cover, and we want to leave as much time as possible for Q&A and discussion. So we'll get started. Again, welcome everyone to this IC2 webinar on the PFAS universe, uses, classification, and degradation. My name is Topher Buck. I am the IC2 project manager here at NUMOA, and I'm going to just run through a couple of quick slides and talk about some logistics for today's webinar before turning it over to Steve and Bob for the presentation. But I certainly want to start by thanking Steve and Bob for taking the time to put this presentation together and to speak to all of us today. My next slide is actually a sort of an agenda slide for the presentation, which I'm basically going to skip over because Steve and Bob will cover this themselves. So sort of on to logistics, you know, as is generally the case with webinars, all attendee lines are muted during the presentation to help us provide better sound quality. You know, if you're familiar with the GoToWebinar interface, there's a chat feature as well as a question feature. So if you have issues with sound quality or something, you know, something you need to sort of notify me about, you can use the chat feature. I would ask that if you have questions related to the presentation, that you use the questions feature for that, not the chat feature if possible. Again, the webinar is being recorded, and we will record the presentation as well as the discussion. And we will post I'll post a recording on the IC2 website on the events page within the next few days, so it should be up relatively soon. I know there's quite a bit of interest in this webinar, and in part because we are limiting the participation to IC2 members and the TURA Science Advisory Board here in Massachusetts. You know, there were others, people who were interested who have been excluded and are looking forward to getting access to the recording. You know, this webinar is somewhat unusual in that we were going to have more time for Q&A than we typically do, which is excellent. Again, you know, please submit your questions through the questions feature. If you would really like to be able to ask a question in your own voice, you can indicate that in the question box, and I will do my best to unmute you when the time comes so that you can simply speak in your own voice and ask your question. I will tell you that for one reason and another, it's not always possible for me to unmute everybody. If you've muted yourself, I may not be able to override that. So I will try. I will try to unmute you if you make it clear to me that you would like me to do so. We're going to, you know, again, we'll talk about this a bit in the agenda, but you know, there'll be a couple of periods, at least 2 or 3 periods for Q&A and discussion during the webinar. I think that's, well, beyond that, I mean, I guess really I want to remind you that, you know, your feedback is really important to us. We do have a post-webinar survey that we would ask you to take a couple of minutes to fill out for us. It matters. to the IC2 training work group as they continue to try and come up with topics and develop webinars that will be of interest to everyone for the future. So beyond that, I just again want to introduce the speakers. We've got Steve Korzeniowski from BeachEdge Consulting for the FluoroCouncil and Bob Buck from the Chemours Company. And I'm going to go ahead and turn it over to you, Steve. Let me make you the presenter here.
All right, I'm awaiting that signal or the shift. There we go. That should work, right?
Yes, that looks good. Thank you.
And Topher, if we're ready to go, Bob and I are ready. Okay?
Yes, please proceed. Thank you so much.
All right, here we go. All right. Bob and I really do thank you for the opportunity to provide information and perspective on PFAS chemistry. Bob and I really do welcome the time that we have today to have a discussion with you, and we do mean that because there are several periods for Q&A. Combined, I guess this shows our age, combined that we have about 60 years, a little bit more than 60 years of experience in this particular area, the Fluorotechnology area. But that said, we're going to cover a lot of material today, as you see. Hopefully it's not too much, but there's going to be some areas that we simply don't have time for. And again, if you see some things that we didn't cover and have a request or have needs, just let us know. As you saw in the earlier charts, we do both work for the FluoroCouncil, but each of us supporting different companies in our efforts. With that, though, I want to go to the agenda. We're going to cover the PFAS universe. Bob is going to do the introduction. I'm going to do uses. This is Steve. I'm going to do uses and some of the questions that Tori asked us. We're going to have time for Q&A. Bob's going to pick up on the degradation and some time there for questions, and then at the end, whatever time we have left, we'll have for group discussion. The reminder, and I told you said this webinar is really for you. Bob and I are here to provide information and perspective, but in the end, we do want to try to help your understanding and answer what questions you have. Before I turn it over to Bob, though, we want to begin with a few messages that you're going to see probably repeatedly throughout the presentation and again at the end. And the Fluorotechnology or PFAS chemistry has a number of core and critical uses that are common to many, many applications, whether it's industrial or consumer, manufacturing, processing, whatever it may be. They also do occur not only as products, but as byproducts, as metabolites and degradation. And I think, one of the key things that we want to discuss and as well as leave with you, though, is that when we discuss PFAS, we do want to be, and you'll see this from Bob a few times, be clear, be specific, and be descriptive, as all PFASs are not the same. And then with that, Bob, I'm going to turn this over to you.
Okay. Hi, everybody. This is Bob Buck. I'm with the Chemours Company. I'm going to take on this first section, and we're going to talk about PFAS and get some grounding and alignment around what we're talking about, how we group them all up, and what it looks like. So, Steve, if you'd go to the next slide, please. So, thought it'd be helpful to start with just a little beginning here. Maybe this is trite for some of you, but when we think about the broadness of categories of chemistry, one area that we all know of that's quite familiar to us is hydrocarbons. And we think about hydrocarbons, they're a really, really big universe of substances of very different kinds of properties and other things like that. And this slide is meant to show that. On the left side, we all are familiar with a polyethylene milk jug. That's a high molecular weight solid polymer, but it's a hydrocarbon. On the other side, on the right, is a gas cylinder for the backyard barbecue filled with propane. That's a hydrocarbon too. But we would never say that the propane was the same as or had the same properties as polyethylene. And in between, maybe just for purposes of preparation for the upcoming Super Bowl, a liquid like ethyl alcohol. For those of you that prefer this particular brand, there you go. But nonetheless, it's an important view to kind of just say, look at the breadth of substances across this space, and we wouldn't categorize them as the same. If you go to the next slide, Steve, the fluorinated universe is similar. to hydrocarbons because, quite frankly, all we've done is replace the hydrogen in a lot of these kinds of substances with fluorine. So starting on the left-hand side, we have solid polymer polytetrafluoroethylene. It's sold for its material properties. It's high molecular weight, just like a polyethylene milk jug. On the right-hand side, we have a gas, a refrigerant gas, HFC 134A. It's getting replaced in cars now, but it's used as a refrigerant in air conditioning systems. Small molecule, just a few carbons. And in between, something maybe that you're all becoming familiar with in our discussions about PFAS, Fluorotelomer alcohol, which is again a liquid in most states that has a lot of fluorine on it and some carbons. Maybe a note here too. I know that many of you may or may not be chemists, so we've oriented this presentation so that you don't have to know a pile of chemistry, but if you can recognize the Egyptian hieroglyphics here and see that there are carbons or fluorines and see similarities and differences, you'll be okay as we tread forward. So, big universes of very different substances. Next slide, please, Steve. So, probably important, as we've all talked about this, and there's so much discussion about PFAS, to reconnect and maybe reground as we begin this conversation today about why are we talking about PFAS. We're talking about PFAS because PFOS and PFOA were originally the substances that were found globally in the environment and in people everywhere. And as a result of that, the questions came rightfully so, asking, where did they come from? And what do we know about things that can break down in the environment to form them, precursor substances? We want to understand them because we believe we need to take action on them. And now, more broadly, we know that there are homologs of these substances, meaning things that have more or less carbon, longer or shorter. We want to know about them and their origin. And now, even more so, we're learning that there are other types of fluorinated species that are manufactured commercially or occur as a result of commercial manufacturing processes. We want to know about them. So the whole reason for creating the PFAS terminology was to help define these groups of substances, identify the specific substances within them, and come up with a common lexicon. And the reason being that that lexicon, the use of that terminology would allow us to be clear and specific and descriptive. So if we were going to talk about propane, we were talking about propane and not including polyethylene. We want to be clear because that's really important. Next slide. No, it didn't advance, Steve.
Yeah, I know, Bob. I'm not sure why. Let's try this. It sort of hung up. I don't have any idea, Bob. It's a good question.
Okay. Well, we were going along pretty well until, electrons don't help us. So, okay, we're going to I'm going to keep chatting a little bit while Steve gets the next slide up.
I'll figure this out, Bob.
As we talk about per and polyfluoroalkyl substances, as we mentioned in the graphic one slide ago, these are substances that include a whole host of things, ranging in very different physical, chemical, environmental, and biological properties. Much like was shown in the slide, where you have polytetrafluoroethylene, a solid plastic on one side versus a liquid or a gas. You can imagine that the properties are very different. So we need to be really, really careful when we're using the term PFAS. It's a very broad term and really should only be used when we're talking about all the substances in this group. And what that means is pretty infrequently. Because generally, if you make statements where you start in the noun in the sentence is PFAS, you have to be really careful what you put after it. Because things like PFAS are bioaccumulative substances is not a true statement. They are not as a big class. There are substances within that group that are, but being more clear, specific, and descriptive identifies those clearly so that not all of these substances are cast in that way and incorrectly characterized. So it's really important to use these terms and be mindful of that. Next slide, Steve. See how we do going to the next one. There we go.
Are we okay, Bob?
Yes, you are.
All
so
right.
everybody,
Sorry about that.
This is all published. It's an open access journal article published in 2011. My name happens to be on it. I hope you have accessed it. It's a bit weighty in information, but nonetheless provides a really good roadmap for how these substances are identified. There are a couple key properties associated with these that are important as we align on what this stuff is we're talking about. The first part, and you can read all the words here, is aliphatic substances. And what that means in the chemical world is carbons linked in a chain to one another. And it's embodied in this little graphic over here on the left where it says CnF2n+1. So it's a chain that has carbons and fluorines in it. That's a really important functional element or functional moiety that's present in these types of substances. Next slide, please, Steve. So let's start disaggregating this a little bit. What's included and what's not? At the time that we posited this terminology and created the term PFAS, per and polyfluoroalkyl substances, it's the substances on the left-hand side of this slide that are in the kind of bluish box that were included. Today's webinar is going to address all of those in great detail around their uses, chemistry, and other things like that. On the right-hand side are substances that are not included. And that's important too. Doesn't mean they're not important from a regulatory perspective or an environmental or a societal perspective. It just means they're not in the PFAS category. And the first area of those is the fluorochemicals, things like the refrigerants, like the 134A. These are substances that have been the focus of regulatory action on a global basis for a long time, beginning with the Kyoto Protocol. There's frameworks, work groups, all sorts of things that deal with those and take care of them. No need for them to be included in this. Likewise, fluorinated aromatics, things where fluorine's on a cyclical bead like this nut that looks like a bolt for a nut for a bolt here. This is hexafluorobenzene, and that circle in the middle lets us know that this is an aromatic compound. That's what chemists know. Fluorine is put on a lot of aromatics, and those aromatics largely are pharmaceuticals, pesticides, and other things like that. Those substances, again, have very specific, deliberate regulatory frameworks, guidelines, and assessment methodologies. They are not included in the category of PFAS. Next slide, please, Steve. Okay, so when the article was published in 2011, this is the picture that was created in order to try to group these things in the proper ways. So the big title is per and polyfluoroalkyl substances. There are two primary categories: things that are non-polymers, small molecules, things that are more water soluble, perhaps more mobile, things like that. And on the right-hand side, polymers. In each of these categories, there are some specific classes. On the left-hand side, for the non-polymers, perfluoroalkyl substances, things that contain fluorine attached to carbon and nothing else other than functional groups. And polyfluoroalkyl substances where maybe some of those carbons have other things on them, like hydrogen. And the reason why they're important is they're the body of substances that are potential precursors for the stuff that's just above them, and we'll talk about that. On the right-hand side, we have three different general classes of polymers: fluoropolymers, high molecular weight materials like PTFE, perfluoropolyether polymers, which you may not be familiar with, but you're going to be after today, with your high molecular weight ether-based polymers, very similar in properties to fluoropolymers. And then the side chain fluorinated polymers, where we wanted to be able to have the surface properties of the two boxes above those, but not the material properties. Those two substances above, the fluoropolymers and perfluoropolyethers, have material properties. They're plastics. They're high molecular weight liquids. The side chain fluorinated polymers have a small amount of a fluorinated chain, 6, 8, 10 carbons, attached to a normal polymer backbone, or so that the fluorinated piece only creates surface properties, and we'll talk about those too. So what I'm going to build forward for you here is how we kind of start fitting these substances into this framework that we've defined as PFAS, trying to be clear, specific, and descriptive along the way. Next slide, please, Steve. In addition, for the purpose of our conversation today, and to advance our collective understanding, we're going to introduce these new images, these icons here, and these terms around how these substances are used. So going forward in this presentation, you're going to start seeing green boxes for things that are raw materials, stuff that's used to build molecules. They're not sold as commercial products, but they're building blocks that are made by industry to create commercial products, which are in the middle, the blue stuff. We're also going to point out terminal degradation products, things that are sort of the end of the road when it comes to these kinds of PFAS substances, things that don't degrade, stay a long time in the environment. Two of them that we all know very well are PFOS and PFOA. So we're going to add in this additional layer of detail and description as we go forward to provide that clear, specific, and descriptive view to you of how these things go forward. Next slide, please, Steve. So let's take that original picture that was in the publication and start putting some things in them, in those boxes from the slide I just previously showed you. So as you can see on the right-hand side, for the polymers that are described within the bigger name of PFAS, they're all commercial products. For the non-polymers, when we talk about perfluoroalkyl substances, those are substances that can be raw materials. Some of them can actually be commercial products, and it's the one unique box where terminal degradation products reside. Because we know that once things have only carbon and fluorine on them, they don't degrade very much in the environment and other places. Underneath them lie the polyfluoroalkyl substances that are not polymers. Those include raw materials and commercial products. I'm going to introduce another layer of specific and descriptive terms here as we start building this out and creating this framework for where things are and how they fit. And those are two of the main manufacturing technologies that are used to make a number of these kinds of substances. This is all very familiar, hopefully, for many of you, because the ITRC fact sheets has been a great resource to help to kind of put some of this together. But the two primary main manufacturing technologies used to make many of these are electrochemical fluorination and the Fluorotelomer process. There are others. We're not going to talk about those today, but these are the two main ones. And you can see the iconography that we've put here to show where substances made by those processes land on this framework of PFAS. Next slide, please, Steve. So the next step I'd like to take you on is, we've kind of said in general what goes where, starting to dig into this being clear, specific, and descriptive. Now what I'd like to do is pick up some specific substances that may or may not be familiar to you and put them in the boxes where they belong. So I'm just going to recite these and then we'll show you where they go. PFOS, I'm going to presume many of you know about that. It's been both a commercial product and it is a terminal degradation product. PFOA likewise. The hieroglyphics here, HFPO-DA is hexafluoropropylene oxide dimer acid. It's the primary ingredient that's used in some things that people often call Gen X. It's a commercial material. There's another material called Adona. It's an ether-based surfactant. That's a commercial material. TFE is tetrafluoroethylene. That's the monomer. That's the building block for the substance underneath it, PTFE, polytetrafluoroethylene. just like ethylene is the building block for polyethylene. Underneath that is FTOH, Fluorotelomer alcohol. It's a raw material used to build Fluorotelomer-based products, one of which is underneath it, a Fluorotelomer acrylate polymer. And underneath that, just for an example, is an ECF-based urethane polymer. So what I'd like to do is show you where they land when we start populating them into this framework and the various categories and classes. Next slide, please, Steve. So here's where they all land. And I've had to shorten up the number of little icons with C's and RM's and TD's because it would have just gotten a little bit too crowded. But as shown earlier, now we have some specific examples, for instance, on the right-hand side, showing all the polymeric materials are commercial products. Here are some examples of them. For those of you who I forgot to put in on the prior slide, the DPTFE, there are specific structures associated with the fluorinated polyethers. There's a D structure. You're going to see it in a little bit, but that's one that goes in there. And then on the left-hand side, you can start seeing where some of the perfluoroalkyl substances land, like tetrafluoroethylene. It's a perfluoroalkyl substance. The HFPO dimer acid is a perfluoroalkyl substance, as is PFOS and PFOA. And then the adona surfactant and the fluorotomer alcohol raw materials are polyfluoroalkyl substances because they have hydrogens on a number of carbons. Not all the carbons have fluorine on them. So what I hope I've been able to show you, and these slides will be made available to you, is how to build forward based off of the framework that's been provided, populate it with known relevant commercial raw materials, commercial products, and terminal degradation products. And how useful it can be when we take a moment to really try to be clear, specific, and descriptive for populating these things, and recognizing that these things are very different. So it's really important to be clear, be specific, and be descriptive. So what I'm going to do now is I'm going to launch you back to Steve. He's going to take you on a little chemistry journey and remind you, oh, sorry. I'm moving too far ahead, Steve. Thank you.
Not yet.
Okay. Sorry. I had a different sheet in front of me. I apologize, everybody.
Not yet. You're not done yet,
anyway,
Bob.
so let's talk about what really matters here, building off that first slide. What we now know is that it's the non-polymer category that is a key focus category. This is one that has been called out by regulators. The substances on the EPA 537 list are all in this category. The substances that have been called into focus by the ITRC and the subject of the fact sheets that they've put together are all in this category, non-polymers. And they're of interest because they're the small molecules. They're the things that have potential for mobility. They're the things that have the potential for degradation and stuff. And we'll talk about that more when we get further down into our discussion. Next slide. So going back to why we're talking about this in the first place, of specific focus we know are the perfluoroalkyl acids, things like PFOA and PFOS and homologs of them, and the substances that may degrade to form them in the environment. Next slide, please. So if we relook at this and look at some of the classes within the PFAS descriptor, we see that there are two classes that we know may degrade to form the PFAS, and those are the non-polymeric polyfluoroalkyl substances and the side chain fluorinated polymers. I don't have on here the icons for ECF and Fluorotelomer, but those apply. So when we think about where the focus should be placed when we talk about PFAS type substances, this starts to create a picture of these are the ones that really matter when we talk about what's present in the environment, what may be present in people, if that's the case, or other environmental matrices that may be of interest or concern. Next slide, please. So let's pull this back up. So these are the classes of PFAS that are really the ones to focus on. What we want to do now is, we're asked, because I know a number of you have read the subsequent publications, the OECD work group published some work with a different picture than this one I've created thus far, with the 5 different classes to identify the framework or map of PFAS. So what I want to do is identify these focus classes on the map that the OECD put forward, and that's on the next slide. So just another way of looking at the same thing. But if we put a little box or a red line around the two areas on the map from OECD, it's the non-polymeric materials in toto and the side chain fluorinated polymers. We're going to talk quite a bit as we go forward about the fluoropolymers and the perfluoropolyethers and why they really aren't and should not be in focus as materials themselves. Next slide, please. Okay, so let's bring this back together and maybe draw the picture again of what the PFAS universe is, and put on the left side those PFAS classes that we want to focus on, and on the right side those that maybe don't need to be a focus because they're high molecular weight polymers. However, and I want to acknowledge this, it's very important, we do want to be sure that on the left-hand side we're including impurities and the use of non-polymer substances like the ether-based surfactants we're going to talk about, like Adona and the HFPO dimer acid. They're used as polymer polymerization aids in making some of the polymers. And those are in focus because they are small molecules. They are in this group on the left-hand side. But the polymers themselves, we're proffering and offering to you that they don't belong because they're high molecular weight and they're stable, and we'll show you some data to support that as we go forward. So now I think I'm ready to turn it over to Steve to talk about the chemistry.
Well, I'm gonna take
Steve,
it from you, Bob. All right, can you hear me okay, Bob?
Yes, sir.
As Bob has already shown you, the PFAS space is really very diverse, and you've heard Bob talk about fluorotelomers, electrochemical fluorination, polymer polymerization aids, fluoropolymers, and perfluoropolyether polymers. And I'm going to elaborate on these in a way that Bob did. I'm going to tell you about what they are and where they go and where they fit and where you find them. The other thing I want to make sure that you understand is that there are other chemistries that are not shown here, like what we call the oxytanes or fluoroelastomers. Not that they don't exist, it's just that we're not covering here today like we talked about at the beginning of our discussion today. So let's start with fluorotelomers. I've got a couple charts, 2 or 3 charts on chemistry, so bear with me. Hopefully it's not too much. Or maybe it's too much or not enough. And so to tell us either way at the end of the discussion. Fluorotelomer business has been around since the early 70s. The chemistry itself was invented in the 60s, but it really wasn't commercial to the 70s. And as many of you are well aware, this was a mixture. This was a homolog mixture ranging anywhere from fluorinated carbons up to 20. With a sort of a heart cut at C6 to C12 for either your fluorosurfactants for the shorter chains or your repellents being the longer chains. We're all well aware of the EPA stewardship program and the major changes that have occurred since 2000 in the United States and elsewhere, where our businesses, no matter what the chemistry that you started with, underwent very significant change, whether with innovation, process reengineering, and in a lot of cases, simplification from homolog mixtures to individual homologs like a C4 sulfonate, or in this case, in the telomer side, a C6 telomer compound. And we've moved to present over the period of the stewardship program from 2006 to 2015 for the FluoroCouncil member companies to short chains being C4 and largely C6. In a pictorial way, in a chemistry way, as Bob talked about a few minutes ago, the raw material that we start with comes from TFE and perfluoroethyl iodide right at the top of the green box to make the perfluorohexyl iodide. And from that comes a variety of other raw materials, the ethyl iodide and the fluorotelomer alcohol that Bob showed you. And then that can be branched out to make either polymers, side chain polymers, or on the right-hand side to make non-polymeric products like surfactants. Characteristic, though, of the Telomer products is that they're even carbons, they're linear, and they're not branched. The other chemistry that Bob talked about was electrochemical fluorination. One of the things that you're well aware of is that there's and Bob let you know this, there's multiple technologies that have been practiced over the years. The electrochemical fluorination is just that. It's an electrochemical cell that produces a variety of products, as you can see here. That's a lot of chemistry, but a couple key messages. Just like the Telomer products, there are non-polymeric products like surfactants, like you see there in the middle. On the right hand and the bottom, there are polymeric products that are derived from these raw materials and intermediates shown on the left-hand side. One of the major differences, though, in this particular chemistry is that because of the nature of how it's produced and the rigor of the electrochemical cell, ECF materials have up to about 30% branched, and that branched material varies by manufacturer and region around the world. And they contain odd and even carbon chain lengths, a bit dissimilar from the Telomer products. Bob spent a few minutes talking about polymerization aids. This is another class of compounds in the list that we showed you. They were developed and are used to make certain fluoropolymers. Not all fluoropolymers, but certain fluoropolymers. They're emulsifiers, and they're used in emulsion polymerization. There are several commercial polymerization aids, 4 of which are shown here. As Bob described, there are the perfluorinated compounds like the HFPO diacid shown at the top, as well as the one with the number 1 there, perfluoro, no hydrogens. And then you have the polyfluoroalkyl ether carboxylates, the Adana that Bob talked about, as well as the number 2 compound that you can see has a chlorine attached to it. So these compounds, these polymerization aids, have taken the place largely of what you are aware of, which is PFOA, and in some cases PFNA. We all do know that the acids like PFOA are still being used in some places around the world, particularly in China and possibly elsewhere. But for the major manufacturers in the FluoroCouncil and most of the other members around the world, these 4 polymerization aids are being used for the major manufacturers to make fluoropolymers. Now, Bob spent a few minutes talking about fluoropolymers in the publication that he and others created in 2011 and where they fit in the classification. Paper that just came out about a year ago, I can say it is a year ago today, is also on fluoropolymers. Barb Henry is a primary author, but the good Dr. Buck, who's on the call today, is a co-author of this particular paper. Now, this is a comprehensive and critical review of fluoropolymers themselves to describe a whole host of attributes and properties of these particular compounds, about their thermal stability, about their biologic stability, about their insolubility in water, about being high molecular weight and not bioavailable, not bioaccumulative. And, it's talking about a number of things. And so should you have a chance, and I think, Bob, this is an open access publication. This gives you a very significant perspective on a variety of fluoropolymers like those shown in the upper right-hand side, PTFE, FEP, ETFE, and so on, about their particular properties and why we have called out that they don't really fit in terms of the microscope or the scrutiny in terms of being available and mobile and so on in the environment, like some of the smaller molecules that we've talked about and we'll talk about today. Class of compounds that don't get talked about a lot are perfluoropolyethylene, PFP, perfluoropolyethers, polymers, and this is some of the basics. They've been around for quite a long time. They have very, very unique properties. They have incredibly excellent thermal stability, chemical inertness. One of the things that has to be taken in consideration, not unlike the other chemistries we talked about earlier, is that there's more than one variety or one version. There are the high molecular weight perfluoropolyethers, but there's also the shorter ones, the oligomers, that are used in a number of coating and other applications, which we'll talk about in a few minutes. These are characterized by having only carbon, fluorine, and oxygen with different amounts, and we'll show you that in just a second. And largely, these are commercial products, particularly oils and greases, used as extremely high-end lubricants where you need high thermal and chemical stability for very severe service or service lifetime, where you might put a pump or something together that's sealed for life, as an example, bearings, vacuum pump fluids, and whatever they may be. Very, very critical applications. One of the things that's to give you some idea of what the structures look like. This is just a variety. There's a numbering, or lettering system. There's a K variety, a Y variety, an M/Z variety, and a D variety. And these kinds of chemistries and structures and properties have been written about and characterized over the years in many different books and journals. Bob, we have a reference right here by Dr. Rudnick. It so happens that it is a small world, because I was his lab mate when I was an undergrad at Rutgers and he was a grad student. We weren't working on fluorochemistry at that time, but it is a small world. I want to switch now and talk about uses. We've talked about categorization, and Bob sort of gave you a picture of the different categories. We've talked about some of the major classes, but what I want to talk about now is where are these things found and where are they used and what are they good for? So you're well aware that carbon-fluorine is a really strong bond, and that bond gives the fluorocompounds, Fluorotechnology, very distinct properties. And we're going to talk about a number of these in some detail, whether it's strength, whether it's durability, whether it's heat resistance, stability, whether it imparts, whether it enables, whatever it may be. It provides some very distinct properties and functions to a variety of compounds. As you saw earlier, they're in many industrial compounds. They're used in manufacturing. They're used as raws. They occur as byproducts. But one of the things I want to make sure that you understand from a reference standpoint is that what we drew on was the ITRC fact sheets, the OECD work, the OECD synthesis paper that was created a few years ago, as well as a FluoroCouncil infographic that I will show you in just a second. One of the things that we really need to do and step back is, and from a broader standpoint, and then we'll get more granular in a second, the Fluorotechnology provides a very large number of benefits that due to the properties that it has, that it enables or imparts, as I said a few minutes ago. And we're going to cover these in the coming charts. Whether it's durability in a variety of these end uses, we're going to cover these end uses, or emission reduction. I'm going to give you some examples of emission reduction that you may not be aware of. Whether it's safety, there's a lot of discussion these days around where these products are used, are they needed? I'm going to give you some examples where they do provide very significant benefit and properties, as well as a number of the electronic equipment pieces that we use and see every day that we may be aware that they're used or we may not be. And this is the infographic. This is sort of a reference document that will be in the charts for you to use. This does not encompass all the end uses. It just highlights a number of the major end uses that Bob and I are going to cover today. So, back to sort of the graphing or the mapping or the legend things that Bob and I have done here today. I'm going to do the same thing. Our goal here today is to help you see where the various PFAS technologies fit in the 5 classes and what is used in the various end uses and that we've just talked about. And this is also going to give you a pretty good frame of reference that you can come back to. So, one of the things that we really need to think about is, and Bob showed you this chart, is where do all these fit? Bob did show you these things. Where do the different fluoropolymers, polyethers, where do they fit in terms of what to focus on and what not, as well as the electrochemical fluorination and the Fluorotelomer technology symbols that you see here. So let's start building this out in terms of uses. We have a fair number of uses, so bear with me. One of the things that we'll start with here, just to give you some examples, is that this is electronics. And so the way to look at, I have 6 charts in that there's 18 different uses, and there's more, but we're giving you sort of a high spot here. On electronics, this technology is due to provide better insulation, weatherability, whatever it may be, helps to touch screens, anti-graffiti, whatever it may be. So you can read the properties. The key here, though, is what we're trying to give you a sense is that underneath each of these applications, the major fluorotechnologies or PFAS chemistries are the fluoropolymers and the perfluoropolyethers, whether the perfluoropolyethers are used as anti-graffiti coatings or whether anti-smudge coatings or for lubrication. There's a variety of uses. In aerospace and defense and aviation, a huge number of uses, whether that's in tubing or hoses or seals, whether that's in hydraulic fluid, whatever it may be, and lubrication. While the space shuttle was operational, many of these high-end lubricants were integral part of the space shuttle systems. And so in this case, you've got the fluoropolymers, which we'll describe some of those uses in a few minutes. The fluorosurfactants are used as some of the corrosion age or surfactant hydraulic fluids, as well as the perfluoropolyethers for lubrication. And building and construction on this particular page, facade protection, for example, protecting facades from light bridges, and some of the paint, some of the coatings are incredibly resistant to the elements, whether that be UV, whether that be corrosion, whether that be the salt air, whatever it may be, as well as wires and cables and paints and coatings. Your high-end paints are engineered, for example, and some of those high-end paints that are used have what they call anti-block. It doesn't stick. They wet, they level, they give you open time so that you can paint and work the coatings. But there's a myriad of applications just in this particular end use. On the first responders, this is a topic that is in the news pretty much every day, particularly because of the AFFF, particularly because of the uses at the various military bases, the use in training in particular, and those materials getting into the water and contaminating groundwater. Used in a proper way, we've obviously learned quite a few things these days about the better use and about this particular chemistry. They provide clearly the best performance, but you have to be careful, and we'll talk about that when we talk about best practices in a few minutes. But in terms of gear, ability to withstand, and whether it's your helmets, whether it's the garments, whatever it may be, protective turnout gear for whether it's police, whether it's fire, whatever it may be, is really important. Alternative energy, protective coatings for various solar panels and whatever it may be, and alternative energy sources, whether it's lithium batteries or fuel cells. Fluoropolymers, the perfluoropolyethers, and the fluorosurfactants are used in that. And in automotive, automotive is an example that I'm going to build out. It is the only one that I'm going to take a few minutes, but they're used in a number of applications that you really may not be aware of. You probably are aware that there may be cases where your seat or the carpet may be protected with a repellent. What you may not be aware of is how integral fluoropolymers are to the operation, the safe operation, as well as the efficient operation of your automobile. So let's take a little bit of journey with the automotive use of fluoropolymers. So you've got your engine compartment, and you can read these, and you're going to have these available to you. You have your transmission compartment and your seals and gaskets. You have your fuel system. You cannot get the kind of mileage you get today without that. And then you get your axle systems, the different bearings and seals and O-rings. You have your steering systems, your PFT bearings, your pump seals, and then you have your suspensions and your brakes, piston seals, and so on. You have your electronics, all that wiring and cables and optics are protected. And then you have your environmental systems. So that gives you a good sense that, how important, this kind of chemistry, and you don't generally think about it or see it or feel it, but it's there. On the military side, you're all probably very well aware that, the protective gear necessary to protect our soldiers, whether it's the clothing, whether it's the helmets, that gear has to be designed to hold up to incredibly difficult and various conditions where our soldiers are around the world. And in addition, we all know that, from a military standpoint, being able to put out fires, whether that's on land or whether that's on shipboard, whether you have an aircraft carrier with airplanes and armament underneath, is a whole different set of desires or needs to be able to get that fire out in seconds and not allow that ship and the people that are staffing it to be harmed. Semiconductor environment, credible need for ultra pure environments, and and the fluoropolymers, the perfluoropolyethers, and the fluorosurfactants provide the ability to create those environments, to create etching materials, to create cleaning fluids for surfactants, and lubrication. The oils in particular are used in the perfluoropolyether oils are used in many of the pumps that are used in those high-end semiconductor systems. Oil and gas, being able to create and have equipment that can go downhole and survive some very, very difficult conditions, whether it's the equipment themselves or the seals or the hoses, whatever it may be. And, you know, I'm not sure how much today, but certainly historically for oil well and natural gas simulation, a number of the surfactants were used, and clearly for lubrication for high-end needs. Fluorosurfactants, the perfluoropolyethers, as well as the fluorosurfactants. In the healthcare and medical end, insulators, I mean, the fluoropolymer paper gives you a good sense that I talked about a few minutes ago, gives you a good sense of some of the end uses and where they're used. But you're probably well aware, you may not be, for surface protection treatments for the medical nonwovens, for the gowns and for the drapes, whether it's the bloodborne pathogens that are protecting the doctors and the nurses, or the gastric juices. I know that's sort of graphic, but these are important things to protect our healthcare providers. In the chemical, pharma, food processing, and general manufacturing, very large number of uses, whether that's pipelining or kettle lining or lubrication, whatever it may be. These particular compounds, the fluoropolymers and the perfluoropolyethers, are used extensively in manufacturing to help keep the kettle material integral so that they don't corrode and fall apart. And they do the job they do, particularly in pharma and food processing. You do not want cross-contamination, and you want to be able to clean your equipment very readily. And outdoor apparel and equipment. We all know there's a lot of discussion these days about what's needed to treat particular garments, whether that's regular textile garments, which I'll talk about in just a second, or high-end performance garments and equipment that are used outside. Clearly, the fluorochemistry, the fluorotechnology, the side chain fluoropolymers allow you to get water, oil, stain, and soil resistance. In the discussion today, and we're going to continue to have it, is what do you really need? If you only need water repellency, do you need fluorotechnology? If you need oil or stain, oil-based stain, what do you need? So this is a discussion and a debate that we're going to have some time. In paper and packaging, this is another topic, as we're all well aware, that's clearly an important subject about what do you need for your food packaging? A number of pieces of legislation. Do you really need oil and grease resistance? Do you really need this? And so this is a discussion that we're having that's going to continue. The industry doesn't know yet of suitable materials to replace all the end-use applications, but the industry is working on it, as you know. The bill in Washington State and elsewhere are looking at, well, what alternatives do we have? For the time being, you have the short chain fluoropolymers that are used as repellents, but you also have not the polymers, but the fluoropolyether oligomers that are used as coatings, the smaller molecules, not really small molecules, but smaller molecules that are used as repellents in paper and packaging. Historically, a number of these compounds, particularly the fluorosurfactants, have been used to provide very significant benefits in terms of wetting, leveling, and polishes and waxes and cleaning products, particularly on the commercial side. And then a sort of a niche application, but still one that's active, is the use as an active ingredient in pesticides, and that is largely fluorosurfactants, derivatized ECF, electrochemical fluorination type materials that are used as particular pesticides in certain places in the world. And then lastly, we did talk about polymer polymerization aids. And again, these are used as polymerization surfactants to make various high molecular weight fluoropolymers. And that can be the acids, the PFCAs, like PFCA, PFOA, either carboxylates, like the four that we talked about and Bob highlighted earlier, and just general fluorosurfactants that have been used over the years. Metal plating and etching, incredibly corrosive, tough environments that require surfactants and compounds that don't degrade under these very severe conditions. They're used as corrosion prevention, they're used in fume suppression. And of course, what we've seen over the years is that where they were used and the emissions from those facilities weren't properly captured, you're seeing some water contamination. And then lastly, a common set: carpet, textile, leather, and apparel, providing whether you need water, oil, soil stain, repel, release, whatever it may be. Two kinds of compounds are generally used. That is the short chain fluoropolymers, as well as the polyfluoropolyether oligomers. So this gives you sort of I know it was quick, but it sort of gives you a sort of a very broad view of, okay, what are the different uses? What are the different kinds of compounds? And then on the right-hand side of each of the chart, which of those 5 particular buckets or categories, where do they fit? And what we've done
Steve,
is that yes, go ahead, Bob.
I'm going to give you a chance to take a drink and interrupt if I may.
Go ahead.
As Steve kind of closes this up, I think it's really important for everybody to understand that the reason why these technologies were all chosen in these various industries was because they looked at all the other alternatives and chose these. So they looked at hydrocarbons and silicones and all sorts of other types of substances to meet the needs of performance requirements, benefits, longevity, and other things that were required in these industries. Rightfully so, and Steve pointed it out, in a number of these use areas, there's been a few steps back to say, wait a second, let's take a look again and see if we really still need these technologies, or perhaps there are other technologies, chemically or otherwise, that provide the function that's needed that could be used as an alternative. So that whole part has been cracked open. What we do generally see is that dialogue about alternatives largely applies to the side chain fluorinated polymers and the things derived from the Fluorotelomers and the ECF. What we see is for those uses where fluoropolymers are deployed and the perfluoropolyether polymers, they're chosen because they very often are so far superior to other materials that are available that even though they're highly costly, their service lifetimes, their longevity, and other things make them the substances of choice. So maybe Steve, just to give you a break, thought I'd interject that, and I'll turn it back to you.
No, Bob. You're exactly right. I mean, both you and I spent many numbers of years not just sitting here doing talks like this, but on the bench, working with customers, doing formulation, whatever it may be. Fluorinated materials, as we know, are often very expensive, particularly in comparison to what you used at the beginning of the presentation, Bob, the hydrocarbons. And in a lot of cases, people tried to use and wanted to use the hydrocarbons, but either they didn't work or they didn't provide the functionality that they needed for their particular end use application. So you're exactly right, Bob. That said, what we've seen, and Bob, you highlighted it, and I have also, is that there's a reexamination of a large number of end uses that I just talked about, making sure that, are we using the right thing? Do we need it? Can we use something else? Can we get away with not having the benefits that we wanted in the past and thought we needed in the past? So Bob, that's a very good discussion, and thank you for the interjection. I was going to cover that in a couple slides, and I'm going to cover it again, but I won't cover it as deep. So thank you for stopping me, Bob. A bit like the infographic, this is, and some of the other things we've given you, this is a single table that we created to try to give you a sense of what the use areas were, as well as what particular compounds go where. And so if you want a quick reference. Before I leave this, I've got just a couple more things to do before we open it up to Q&A for the first round. I do want to talk about best practices, because Bob and I both have more than just alluded to this. Things have changed. And the major messages, whether it's from AFFF and the Firefighting Foam Coalition, or the textile industry on the right-hand side, is that we are strong advocates of using a product only when it's necessary. Use only what you need. Reuse and recycle. I mean, don't throw it out. Minimize waste and emissions. Capture and dispose of everything properly. Some of you may have been had the opportunity to participate. There was a webinar yesterday that OECD gave that Tom Cortina and Mitch Hubert talked about the Firefighting Foam Coalition and best practices for AFFF. So both of these particular markets or end uses, whether it's firefighting or did my screen sharing get paused? Is it still sharing?
You can still see it, Steve.
All right, yeah, I just got to note that, but so yes, it is really important that we do pay attention and we continue the discussion of do you really need this chemistry? Where does it provide use? And I think that'll take us to a good place. Bob, Bob and Tuffer, what I want to do is I want to finish up with a couple charts, and then we're going to open it up. Tura and Turi and the Massachusetts folks asked us a number of questions. They asked us about the fluoroethers and polymerization aids, which we've covered, but they also asked us about two other things, and they wanted to talk a little bit about some of the alkyl acids like the phosphonic and phosphinic, and they also wanted to have a little discussion on the EPA program. And I've got one chart on each, and then we'll have questions at that point. So the first one is the phosphonic and phosphinic acids. Very not really well known. I mean, they're known. People talk about them, but they're really much less well known, less studied, and clearly less used acids that were made historically by more than one company, a couple companies. Bob and I discussed this, at length. Current manufacturing uses are expected to be really small, but if at all, we're not, Bob and I at least, given our contacts out there, aren't aware of many, if any, uses of these particular chemistries, though they were used in the past as defoamers and pesticide formulations and as some wetting aids in consumer products. But what Bob and I are not aware of is, how pervasive that use is now, but they did exist. And I drew most of my information from the particular paper cited down here at the bottom from Environmental International from Dr. Wang. But again, I wanted to address it because, again, it was a question that was asked. And I want to finish before we go into Q&A to EPA's process. We get a lot of questions around the EPA process and, about our chemistry, the Fluorotechnology and the different compounds that have entered into the market with PMNs and TSCA approval and so on and so on. And this has been going on for many years, but this changed very dramatically, as we all know, once 3M made their announcement and the analytical chemistry and the biomonitoring and the regular monitoring found PFOA and PFAS, in every place they looked. So the goal was to change the chemistry, to create a chemistry that had a better footprint, for want of a better word, a more sustainable, less toxic, a more acceptable footprint than the chemistry that we had used in the past. What EPA did, and this particular set of burger dots, there's four of them here. Many of you know Tony Krasnick and have heard him talk, but Tony was an integral part of the program for all of us and many of you working with EPA over the years to try to get some new chemicals through the process. And Tony gave a lot of talks, and this came from one of his talks that's cited here below in 2013. The EPA did take a very integrated approach, an integrated testing approach, where they really mapped out a whole set of data needs. Not every company got each data need, but what EPA did is they created a matrix, and they wanted to fill in that matrix with a very large amount of data, that whether it was tox, whether it was metabolism, whether it was environmental fate, whether it was degradation, half-life, whatever it may be, they created that matrix. And so before our particular industry was permitted to put compounds on the market, the short chains, for example, work was required on either the notified substance of whatever the product was, and or the degradant. The degradant, for example, on a short chain area would be for perfluorohexanoic acid, as an example. And what EPA did is they required companies to do work, and then once EPA said, well, this product can go on the market under these specific uses and exposures and manufacturing levels and so on, The so-called consent order, the 5E consent order, which guided what companies had to do, did not expire. Those 5E consent orders are still active today. EPA does have the wherewithal and the right that if they find data, companies or others that generate that is not acceptable, EPA has the right from an enforcement standpoint to pull those products. And alternative testings, the testing on these particular products is still ongoing today. So Bob and Topher, I think what I want to do at this point, I want to stop and give folks a few minutes. We've been going on for about an hour between Bob and I to ask questions before we go on to the last section, which really talks about degradation, which was the last major topic that we were asked to cover.
Great, thanks, Steve. So yeah, I've gotten several questions submitted through the question box, and I'll just read these out. Let you respond to them. The first one is just a very short question, which is essentially, and I'm paraphrasing slightly here, but essentially, the question is: so PFAS compounds are not all bioaccumulative, but are they all persistent?
I'll take that one, Steve.
You go ahead, because I know you're going to get it right.
Yeah, this is Bob. We're going to talk about degradation. The answer is no. All PFAS substances are not persistent. Many of them do undergo degradation, particularly the Fluorotelomer and ECF-based substances. What we do know is that they can and often do lead to highly persistent terminal degradation products, like the perfluorocarboxylic acids that I highlighted earlier, and we'll talk about that in a moment. So yes, we know that quite a few of the substances do undergo degradation. The fluoropolymers and the perfluoropolyether materials that are the high molecular weight materials, as we pointed out, and we'll come back to those are rock solid stable.
Okay, great. So next question. Refrigerants and fluorinated aromatics are not considered PFAS, as you described. However, some refrigerants, such as R134A, are used as propellants. So the question is, why are refrigerants carved out of the PFAS classification, and would the use of R134A as a propellant be considered a PFAS?
Yeah, that's a good question. The uses are not part of the qualification to define whether a substance is a PFAS. It's its chemical structure. So 134A is not a PFAS substance, no matter what its use is.
All right, great.
It's not by the categorization we created.
Right, understood. Okay. Where do all the chemicals with other functional groups or copolymers fit in your 5 categories? So, for example, fluorinated siloxanes, aromatics or cyclic compounds with fluoroalkyl chains. Do they result in other terminal degradation products besides the familiar PFCAs or PFSAs? Carboxylic acids or sulfonic acids, that is.
Yeah, that's a good question. Steve, I'm going to keep rattling these off if that's okay.
Yeah, and I'll add to it if necessary, Bob.
So the fluorinated siloxanes definitely do fit. They will be in the category of either perfluoro or polyfluoroalkyl non-polymeric type substances in general. And again, because of that perfluoroalkyl moiety, to the extent that that moiety can be severed from that siloxane backbone, it goes down the same pathways toward the carboxylic acids or the sulfonic acids. As I mentioned earlier, the aromatics are excluded in toto in this discussion. So anything where a fluorinated alkyl chain, whether it's a CF3 group, a fluorine itself, or a smaller chain fluoroalkyl is attached to an aromatic moiety, for this consideration thus far, we've said it's not in. We've certainly heard from, in the dialogue within the OECD, a number of regulators who have interest in fluorinated aromatics. And of course, if that's an area that's of interest, it can and should become a point of discussion. But within the current terminology of PFAS, because it's aliphatic, the aromatic substances are excluded.
Okay, great. Let's see. Since the final degradation PFAS are persistent and are highly mobile in the environment, proper disposal is important. But what is proper disposal? I'm actually wondering if this would be a good question to talk about when we get to degradation products. But maybe
Topher, what I might say is, can we hold that one? I think let's go through our degradation. Sure. Let's circle back to that.
Yeah, I think that makes sense too. Sorry, so let me, well, so here's another one. Can you please talk a little bit about the purity of the polymers? Are there non-polymeric PFAS in the final commercial polymer products?
Sure. Steve, you want me to handle this one too?
Yeah, go ahead.
Okay. So the answer is in some of the final polymer products there are. It depends on what form they take and how far they've been processed. Many of the polymers are sold as pellets, and residual polymer polymerization aids and other things are pretty much out of them. And then again, when they get used in an industrial setting, because of the high temperatures that are often used to apply those polymers and process them, those small molecules thermally are decomposed. So the good example I might point out is in the paper that we shared with everybody in advance on fluoropolymers, the use of these substances in medical applications is pretty pervasive. And one of the really critical criteria is extraction testing and other things looking for anything, fluorinated or not, that might be residual in those polymers after they've been applied to medical devices. And one of the criteria, of course, is that there can't be any significant amounts that would be deleterious. And in that paper and the supplementary information, an example is provided where you can do extractions and you just don't see anything at all. So there's no question that in the creation of these substances, impurities get formed because that's just part of what happens. What we know is important to focus on is the downstream processing of those to be sure that those impurities are captured and destroyed. Different companies are taking different approaches. The company I work for is moving down the path of capturing all this stuff either to reuse it and recycle it, because once you make carbon fluorine bonds, you don't want to waste them, or you destroy them and break them back down to where their carbon fluorine bonds are broken.
Bob, it's Steve. It's fair to say that in some cases, you know, when you go through your processing of the polymer, there's a sintering step that makes sure that anything that's small gets destroyed and captured and taken out, correct?
Yes.
And I assume that would apply to unreacted monomers as well as other, you know, whether it's oligomers or other small molecules in the polymer.
Yes.
Okay. And then a related question is, people are wondering if you could just talk a little bit about for those, like for the extraction studies that you were referencing, do you happen to know what the detection limit for those studies is and what solvent or solvents are used to do the extraction?
Regrettably, off the top of my head, I don't. But what I'll say is, Topher, I think we provided 3 publications to the group as light reading material in advance or after this webinar. And the paper that is the one on fluoropolymers is open access, and the supplementary material information is also free, and those details are provided in the supplementary information.
Great, thank you, Bob. So we're at quarter past. I mean, there are more questions and more questions coming in, but I don't want us to spend too long here and then not have time. Clearly, you know, a number of the questions that I've gotten that I haven't yet asked including the one that I started to ask, are focused sort of on degradation products and related issues. So I just wanted to check with the two of you about should we take a couple more questions, or do you want to move on to the next part of the presentation?
Well, why don't we do this? Is Steve. Bob, I'll step in here. Why don't you let us move through Bob's next part? The degradation is a really important one, and ties a lot of this together. There'll be plenty of time to have a lot of additional Q&A as we finish. Would that be fair, Bob?
Yes.
Okay,
I only have. Go ahead, Topper. I'm sorry.
No, I was just gonna say that sounds good.
All right, I only have one more chart, and that's trying to answer some of the additional questions that we did get. And you don't see. Oh, I lost my sharing ability. Or am I sharing? Am I still sharing?
You're still sharing, but it's back to the first slide. There you go. You got it.
Yeah, technology is wonderful. And there's no answers to these questions written, but the first question here is about global restrictions. I would refer to ITRC. ITRC, as you know, is doing a tremendous job looking at different restrictions and different exemptions and different rules and regulations. And so I would refer the OECD diagram, the one that Bob showed. There is a lot of discussion about, is this the right classification? Bob talked about that today. There's a lot of different ways to look at this. This is being looked at by Jianwen Wang, and who was one of the primary authors. Bob is involved in this, and many other folks are looking at do we need a reclassification? Do we need to add things? So it's a work in progress. And then the last one, there's a list, OECD spreadsheets of different substances and so on. The FluoroCouncil and its members are actually actively working on this particular list. So that's the best way I can answer this request. If there's more information needed, we will certainly try to provide it. And with that, Bob, I would like to turn this back over to you and finish up with degradation.
All righty. Let's talk about what things can turn into. Next slide, please, Steve. So just reconnecting with the words we received about the asks about what things can turn into. What I will say is I don't think our time today permits us to go into a huge amount of detail around quantitative amounts of things, half-lives and stuff like that. There are a large number of publications behind a number of things I'll mention, and if there's specific questions, we'll answer them, and we can provide some guideposts if folks need them. Next slide, please. So what I'm going to do is I'm going to come back to the framework and the picture that we formulated earlier in our discussion today, and look at the 5 different classes of PFAS as we consider degradation pathways in these dimensions. The biotic dimensions, both aerobic and anaerobic, and abiotic mechanisms, thermal or heat-related, light, chemical, mechanical, hydrolysis. But I will put an important bounding thought around this. It's really important as we think about degradation pathways that we put them in the proper context. And that context has to be built around how those substances are actually used in their life cycle, where they actually can and do become present in the environment, and relevant, realistic environmental conditions for degradation. There are lots of studies that query inherent biodegradability by really pounding on things. That applies too, but I think it's really important that we don't forget that it's the conditions under which we think things can realistically occur that are important as we assess potential for degradation. Okay, so I'm going to take on abiotic degradation by thermal means first. Next slide, please. So what I believe we know scientifically about thermal degradation of per and polyfluoroalkyl substances is that under typical municipal or medical waste incineration conditions that are regulated and specified around the world, that PFAS substances are destroyed to form HF and CO2. It's really important. This is a good one to calibrate us on realistic. This doesn't count throwing things into a can in the back of your property and setting them on fire with a match, because that's dangerous no matter what the substances in the can are. They don't have to be fluorinated. But under reasonably foreseeable use and conditions, meaning that the products that are here typically would go to facilities that have measured temperatures and things like that, and at least the limited, if not sufficient amount of data that's available suggests that under thermal degradation conditions that are properly managed through the life cycle, that the fluorinated materials are destroyed. Okay, next slide, please. So the next thing I'm going to do is I'm going to dig into three of the specific boxes, the perfluoroalkyl substances, the polyfluoroalkyl substances that are non-polymeric, and the side chain fluorinated polymers. And we're going to talk about the two general kinds of classes of substances within the Fluorotelomer-based substances and the ECF-based substances. So let's start off with fluorotelomers. Next slide, please. So when we think about degradation pathways for fluorotelomer-based substances, and here I'm calling out the short chain ones that are based on C6, what I thought might be helpful is to provide this pictorial showing what some of the representative substances in these various classes are and their role in the uses. So for instance, the perfluorohexyliodide that you saw in an earlier chart, that's a raw material. Perfluorohexanoic acid is a terminal degradation product. Not a raw material, it's not used to make these products, it's not present in them functionally, it's a degradation product. For the polyfluoroalkyl substances, the telomer iodide, the 6,2 iodide, the 6,2 alcohol, those are raw materials, building blocks for making things like fluorotelomer-based surfactants, which are the product level type stuff, the commercial substance level type things in these polyfluoroalkyl substances category. And finally, in the side chain fluorinated polymers, we attach that 6,2 fluorotelomer group to a polymer backbone like an acrylate or urethane, and that's what makes these side chain fluorinated polymers, where you can envision that 6,2 piece is sort of like the tine on a comb. The comb's backbone is an organic polymer, but the tines are these fluorotelomer chains kind of sticking up perpendicular. So let's take a look at what happens when we think about degradation of these substances, and we'll go into that on the next slide. So I've chosen to focus on biodegradation here, and I'm going to comment on the other dimensions as part of my discussion. So for the most part, the yields will vary depending on the duration, the time and the temperature, the concentration, the medium, and things like that. But in general, the short chain fluorotelomer-based products and raw materials all, if they degrade, form the same set of transient biodegradation intermediates generally. And here's some hieroglyphics of what some of those are. We can talk about them if you want to. And those substances, under appropriate conditions, most notably aerobic conditions, will form the terminal degradation products shown here, which are the short chain perfluorocarboxylic acids ranging from 4 all the way up to 7, with the perfluorohexanoic acid being a predominant one. Now, that said, it's going to differ depending on what goes where. We know that under anaerobic conditions, where we don't have a lot of oxygen, that many of the transient biodegradation intermediates, the processes stop at those. If aerobic conditions are then presented, they'll go on and degrade some more. And there's all sorts of differences in the sorptive properties, the potential for mobility of all of these substances. It would be a separate 2-hour seminar just to go into the fluorotelomer-based stuff. But there are quite a large number of publications that talk about these things. I talked about thermal from an abiotic perspective. We know that hydrolysis is really important That's one of the important steps for any of these product level species to form some of these transient intermediates, most notably the 6,2-fluorotelomer alcohol by ester hydrolysis. That's really important. We don't see a lot of information suggesting that photolytic processes are really important for these substances, but we know that photolysis can and does degrade some of them if they are present in those conditions. The question is how often and how frequent are they in those conditions? Not quite so sure. From a mechanical perspective, really don't see any issues there. From a chemical perspective, my personal view is there's not a lot of published work, but that's a lot like hydrolysis. So if you can chemically degrade these things, they start cascading into the same biodegradation pathway that we show here. From an atmospheric perspective, the products themselves are not really of concern atmospherically. We did a ton of work about a decade ago on the atmospheric processes around things like 6,2-fluorotelomer alcohol. And what we showed was that for the most part, the massive amount of that substance is mineralized. There's a potential for small amounts of the perfluorocarboxylic acids to form as a result of atmospheric degradation, but the majority of the substance is degraded into fluoride and CO2. Okay, next chart. Let's talk about the electrochemical fluorination-based substances. And I will refer you, as you go back and look at your notes from our discussion today, to the chemistry slide that Steve showed earlier, and you'll notice that the ECF products have a different order of things as far as what comes after the carbons that have fluorine on them. So when we think about representative types of substances in this particular chemistry, again, from a perfluoroalkyl substances perspective, we have things like the sulfonyl fluoride. That's a critical raw material. I've called out the octane sulfonyl fluoride here. It's got 8 carbons. It could be the butane, which is 4. That's more commonly practiced today by some of the leading producers. Things like PFOS and its homologue PFPES, butane 4, they were and are both commercial products and terminal degradation products. And as Steve mentioned earlier, it's with perhaps a degree of remorse that we still have to talk about. There are significant manufacturers of PFOS in other places in the world outside of the Western and other countries that have made firm commitments to stop that technology from being produced. The polyfluoroalkyl substances, the N-ethylphosy, that's sort of the equivalent of 6,2-fluorotelomer alcohol, raw material building block, and then that can be used as well as other things to build surfactants and things like the polymers shown on the bottom. Next slide, please. Okay, so when we talk about electrochemical fluorination-based substances, today the short-chain substances are largely based on the butyl chemistry, C4, but I've included a perspective for the longer chains because historically we're still just seeing them present in so very many places. But again, much like the fluorotelomer-based materials, the ECF-based products and the raw materials to make them, once the first steps in degradation occur and the fluorinated functional part is carved off of a surfactant or a polymer, they have the same basic set of transient biodegradation intermediates. Lots of acronyms here. You can look these up in the 2011 terminology paper or in the ITRC guidance. There are some really good pictures in some of the fact sheets about the degradation pathways and how they proceed through these substances. Some of these substances can be found because they stop and linger around a little bit, but for the most part, the terminal degradation products, what they ultimately become when oxygen can do its job, is sets of perfluoroalkane sulfonic acids and the perfluorocarboxylic acid, because most of these ECF-based products do contain some impurities around that have the carbon piece in there. The PFCAs come into play more so in the ECF chemistry due to the atmospheric degradation processes. because these intermediates and things like the N-ethylphosy that I showed earlier, that's the fluorotomer-alkyl equivalent, they don't degrade in the atmosphere to perfluoroalkane sulfonic acid. They degrade to perfluorocarboxylic acid. So they contribute to those also, and many of those substances are still found in some atmospheric measurement, and again, they're being produced, particularly the long-chain ones, in places like Asia. So the same general tenor applies to these, much like the fluorotelomers, depending on whether you do a ready biodegradability versus an inherent biodegradability test, depending on which soil you choose, which sediment you choose, which activated sludge you choose, the duration of your study, the nutrients and things, the yields and other things can and will vary, but the general flow of things is the same, in my opinion, based on the science in all of them. Okay? All right, let's move on and talk about the next box, the perfluoroalkyl substances. And this one's going to be easy. For the perfluoroalkyl acids, of which the 4 general types are described here, these are generally not easily degradable substances, particularly the carboxylates and the sulfonates. They are really stable. They don't undergo biotic or abiotic degradation that we're aware of. You can destroy them thermally when you heat them up hot enough. And Steve mentioned earlier in some of the processing of things that those kinds of temperatures are reached. And in fact, there are published studies, for instance, showing that the ECF-based materials that might lead to things like PFOS or the sulfonates, when you incinerate them, they do degrade. So it's hence my point earlier about why these are the kinds of things to focus on and those substances that can degrade to form them. The one thing that I might point out in this area before we go on is, as we think about clear, specific, and descriptive, there is no question that even within each of these categories, the substances that are present in them have different properties. We know, and there is well-published data showing that the carbon chain length in these categories makes a huge difference in the physical, chemical, and biological properties of these substances. And one of the references that we shared with everybody, I know it wasn't the subject of today's meeting, was a recent publication looking at perfluorohexanoic acid and showing that its toxicology profile, leading to a reference dose for humans and at least some estimates of what safe levels could be in environmental matrices, is vastly different than PFOA because its properties are vastly different. So it's really important, even within these, to not cast them as all the same. So to the question that was posed earlier, we know that not all PFCAs are bioaccumulative. The short chain PFCAs are not. And likewise for the PFSAs, the long chains most definitely bioaccumulative, the short chains are not. So it's important to make those distinctions, and again, not overgeneralize to a point of perhaps being incorrect. Okay, next slide. So let's talk about the couple polymer categories that we've said throughout this presentation today merit being set to the side because of the polymers themselves, not the impurities, not the processing aids. We know those need to be paid attention to, but the actual polymers themselves. And I'm not going to go into great detail on the fluoropolymers. This is a repeat of the slide earlier. There's lots of data to show that fluoropolymers are stable within the range of their foreseeable use conditions and environmental conditions. I do want to point out one area, though, on fluoropolymers that I think it would be neglectful not to raise up because of the widespread understanding of it. I'm not an expert in it, but I'm going to call it out, and that's on the next slide. We know, and it's well documented by the industry, and this is an example of a document from Plastics Europe. There is one from the Plastics Industry Association here in the U.S. that acknowledges and points to the great importance of proper use and handling of fluoropolymers and the issue of polymer fume fever. We know, and others do know, that when you thermally process fluoropolymers, that there can be some fumes that come off of them. And in an industrial setting, adequate ventilation must be spec'd in to handle that. In a non-industrial setting, the only time that we know of where polymer fume fever occurs, at least that I'm aware of, is when the polymers are heated above their thermal decomposition temperature. And the most obvious example that people have called out over the years is nonstick cookware. When you put a nonstick pan on top of a stovetop and it doesn't have the right things in it, or it's overheated to the point of actually starting to decompose not only the food in the pan, but the pan itself, the polymer can degrade and form volatile substances that are actually and can be harmful. And birds are particularly susceptible to inhalation toxicity. So there have been lots of cases where fluoropolymers that have been heated well beyond their foreseeable use condition, they've been thermally degraded because the heat was left on, that bad things happen. And I've just put in this as a reference. This is probably one of the most current ones. The Plastics Industry Association in the U.S. is just finishing up an update in 2019. Glad to share that when it comes through. But there's a wonderful recitation in this link about polymer fume fever, about processing and other things like that, that if you're not familiar with it, may be a helpful and useful reference and information point for you. Okay, next slide, please. This is, again, maybe a bit of a repeat from before, too. The perfluoropolyether polymers, not the oligomers, those are much smaller molecules that have poly functionality on them. But the perfluoropolyether polymers have very similar properties to the fluoropolymers. They are just rock solid stable as long as they're not heated above their thermal decomposition temperature. They're not water soluble, they're not soluble in any hydrocarbons, and as a result, they really can't move around the environment because they don't have a means by which to do that. They're not volatile. They have incredible thermal, chemical, photolytical stability. Steve pointed out these are the lubricants used in all of the sensitive parts of high performance engines, in aircraft, in automobiles, in equipment in facilities and stuff, where the machines will operate at really high temperatures and they need the stability and the longevity. These things are sort of like that Energizer bunny. They just can, as long as you don't get above the thermal decomposition temperature, they just keep on going. And for a lot of folks, what that means is their maintenance schedules are so much easier. They don't have catastrophic failures of equipment because other types of lubricants degrade. And the easy way that you know that that happens is that bearings and other things fail. And that's really bad if you're running and manufacturing equipment or operating a plane or a car or a train or anything like that. Okay, I think we're at the end of the piece where we just kind of touched on, again, this was more of a higher level discussion about degradation pathways. But Topher, I know you said you received quite a number of questions, so let's dig into those and we can provide a little bit more exploration in response to those questions.
Great, thank you, Bob. So first I'll go back to the question that I started to ask earlier, and I'll ask it again. Since the final degradation of PFAS, I think it's essentially supposed to say since the terminal degradates of PFAS are persistent and are highly mobile in the environment, proper disposal is important. What is proper disposal? Hazardous waste landfill, incineration, both have environmental justice implications. And so the question fundamentally is, are the members of the FluoroCouncil willing to develop proper on-site disposal options like was done for chemical weapons?
think that's a good question. I'm not sure I can answer for the FluoroCouncil, but I think we can certainly take that question under consideration. I think it's important to think about, what's really necessary and needed. What we said is in a lot of the industrial uses that, excuse me, capturing the industrial wastes and securing them in a secure landfill or incinerating them makes a lot of sense in a number of cases. I don't know, Steve, if you want to comment on that.
No, I mean, Bob, we recommend incineration, but I think Taffer's question is a good one. We will need to take that back to the FluoroCouncil members. There's been a number of technologies that have been developed that allow you to separate and segregate the fluorochemical portion from like whether it's an AFFF waste stream from a fire, fire water, whatever it may be. There are technologies in coagulation and electrocoagulation and so on, and then incineration of the fluorinated part by proper means. So yeah, Tuffer, I think it's something we're going to have to take back and discuss further, and try to provide you another answer other than incineration, because again, we all I think believe the incineration capacity globally is limited. It is efficient if it's done effective, if it's done correctly. But are there other means? And we know from a scientific standpoint, people are working on destructive technologies. We know that, whether it's sonication, ultrasound, whatever it may be, and other chemical means that they're working on it. But there's no ready solution other than incineration today.
Right. Okay, good. So I'm gonna kind of try and combine a couple of other questions that stick with this theme of incineration. So if you'll permit me, I'm going to read a couple of questions, kind of just mash them together and let you take them as you will. So, the first question relates to incineration of PFAS compounds like surfactants used in AFFF. And fundamentally, the question is, since these are chemicals that are used in fire suppression, what happens to them in an incinerator? And are there any data, stack tests and the like, that describe, the consequences of burning materials like AFFF in a regulated incinerator? And then related to that is the question, do you have any information about the breakdown products of these chemicals, in fires, i.e. not incinerators, right? So I think that's whether, potential exposure to firefighters or PFAS chemicals that are present in a home that burns. So yeah, kind of lumping stuff together there, but.
Toffer, there's lots of questions in that question.
Understood.
But you want to start, Bob, and then I'll finish?
No, please go ahead, Steve.
I mean, as industry, we did some work in the early 2000s as an industry in cooperation or direction or whatever you want to call it with EPA under what they call an enforceable consent agreement, where we had to put together, and we're not the only ones to do this. Bob had mentioned other people have done incineration studies, where we had to do a very controlled set of incineration studies to look at the various conditions about what happens in regulated, high hazard municipal incinerators that, operate at the way they're supposed to. And we had to measure everything coming out of the stack. And it was mineralization. There was no PFOA and other materials. So done properly, these materials do get mineralized. As Bob did say, if you have the potential for incomplete combustion, you're likely going to have fragments. And so that might force you, if you've got fire water, for example, which is what you're talking about, that's got combustion products, that's got fuel, it's got whatever it may be from that fire in particular. There are other technologies that are, if not commercial, certainly pilot available. There are commercial technologies, I believe, that will segregate, coagulate, whatever it may be, and then you'll collect the fluorinated fragments. And then you can incinerate those and concentrate them. So there are ways to do that. So it's possible that if you're incinerating under non-optimal conditions, you're going to get fragments. The key is then to take that water and further process it, which again, technology is available. to collect that and then incinerate that material.
So Steve, if I may, Topher, I'll just add a couple thoughts in on top of this, because these are really important questions. Thank you for asking them. I think the key thing is, in an incinerator, even the fluorosurfactants will be destroyed, and because they don't provide fire suppression in an incinerator. Their function is completely different, but they'll be degraded. What we do know, and I don't know of too many papers, but there's certainly been lots of research done on products of incomplete combustion, even of hydrocarbons, to show that they're dangerous. Backyard fires and other things like that. Luckily, in most buildings and other places like that, the fluorinated parts are a really, really, really small part of what's there. All that other stuff burning is just as hazardous, or perhaps even more so, than what could be formed from the fluorinated bits, unfortunately. I don't know of a specific study looking at products of incomplete combustion for fluorinated materials. We'll have to look into that.
That's great. Thank you, Bob. So in effect, I think what I'm hearing, and this certainly jives with my understanding as a chemist, is right that even though we may think of a fire like a hydrocarbon fire as being, a very hot fire, it is qualitatively different than a hazardous waste incinerator, for example, right? So I think in effect that's part of what you're saying.
That's correct. Yes.
And maybe
the temperature just doesn't get to the high enough level. Actually, that's why incinerators are spec'd to run at certain guideline minimum temperatures. And because we're getting a number of questions, sort of related to this theme. Maybe another way of asking this is, are there any PFAS chemicals that you know of that are not destroyed in an incinerator? Again, assuming it's being properly run.
Well, the work we did was. Go ahead, Bob.
Yeah, not that I'm aware of. I will say this, Topher. I think I'm glad the questions, but I'm going to make sure to caveat. Steve and I are not incineration experts. There are other people that know a lot more about incineration than we do. And again, this may be a topic for a future discussion, but that's what we know. That's what we know.
That sounds good. So I'll move on if that's okay, just so we can try and cover a little more ground.
Sure.
We still have plenty of questions. So let's see. Switching gears a little bit. One question is just about the definition of short chain chemicals. So basically, the question is the definition of short chain as C6 and below versus C8 and below dependent on the process used to produce the chemicals?
Yes. And thank you for noticing that. We didn't really dig into the short versus long chain, but what we know is that the dividing line, the number dividing line for short versus long chain is different for things like perfluorocarboxylic acid versus perfluoroalkyl sulfonates. So we often look at the Fluorotelomer process and say C6 is short chain because it's linked to perfluorohexanoic acid, a short chain acid that has the properties I talked about earlier. But for the ECF process, short chain is 4 because in the ECF process, the 6 material has the same properties as PFOS as far as bioaccumulative and other things like that. It's classified as long chain because of its biological and chemical behavior.
Correct.
So sorry about that bit of confusion, but if there's a need for that, we can certainly point toward resources that help elaborate on that in a little bit more detail.
It's a very good question. Yes, thanks.
Okay, great. So we've gotten at least 2 questions, basically the same, just asking if you can, are there typical decomposition temperatures for fluoropolymers, right? This is sort of relates to the last slide or 2 that you were talking about, Bob.
Yes. There are handbooks, much like there are handbooks for all sorts of polymers, that talk about what the thermal decomposition temperatures are for all of these types of polymers. There's like a polymer handbook that says, here's what the thermal decomposition temperature of, ethylene tetrafluoroethylene is versus tetrafluoroethylene made by this way or that way. Again, we can, to the extent that folks want to know that, we can point towards some resources. That's all cataloged because material engineers need that fundamental data in their material selection choices, so those things have been well compiled.
Do you have, well, I guess I am trying to put you on the spot. Like, can you give even a general sort of range? I assume we're talking about several hundred degrees Celsius.
Oh yeah, some of them will go up to 400 degrees centigrade.
Yeah.
Stable up to 400 degrees centigrade. Some of them are only stable up to a couple hundred degrees centigrade. So over a pretty wide range.
Okay, thank you.
And not surprisingly, it's based on their chemical composition. The things that are perfluoro are always much more stable than the things that are polyfluoro.
Makes sense. Okay, so switching gears a little bit again, the next question is essentially, what's your opinion on the proposed mobile and very mobile rules in Europe, saying that bioaccumulation is not required for a short-chain PFAS to be hazardous due to extreme persistence and mobility?
Great question. It's a debate that, Bob, you and I can talk about this. It's definitely an ongoing debate, as you know, because what happened is that we went from PBT to PMT, and it created quite a bit of discussion with, from what I understand, Bob, no current resolution of what the right definition of M is here in classification. That's my understanding of the current art. Is that correct?
I think so. Shall I jump in?
Yes.
So my personal view, looking at it scientifically, is I think mobility is a great criteria to consider. But I think it's an and statement, not a singularity. I think even thinking about PMT is okay, but don't forget the T part. And I think the real challenge that's coming for folks is to think about, as Steve laid out, what's the right way to, if I may use my mantra earlier, clear, specific, and descriptively to, say what the M criteria is, and then how it flanges up with the P and the T criteria. Because I can remember sitting at a CTAC meeting in Brussels a few years ago, and Steve actually was there too when this came up, and folks started saying, well, wait a second, what about things like calcium and other things like that? Maybe this is a bit facetious, but you have to be really careful about laying down criteria about persistent substances and defining what you're talking about. So I think it's a good discussion point, and if it helps meaningfully identify substances that truly are of concern, then we all ought to be for it. But we need to have good, sound scientific criteria and decision-making behind it. Thanks for asking.
Great. Okay, let's see. Here's another one. Again, sort of switching gears. Can you just describe briefly? You referenced the fact that PFAS chemicals are used in biocides, pesticides, and essentially the question is, what is the function of those PFAS chemicals in biocides? Are they used as surfactants, or are they part of the pesticidal action itself? And I think you reference them as being actives and not adjuvants, so I assume it's the latter, but maybe you could just clarify that.
This is Steve. So there over the years there have been a few uses of fluorosurfactants that have acted as dispersing agents. The bulk of that is largely gone for pretty obvious reasons. But whether it's fire ants or red ants, whatever it's called in South America or Brazil, a functionalized ECF surfactant is an active ingredient that interrupts various biological pathways. So it's a pesticide.
Yeah, Steve, let's call out Topher. Folks will know what it's sulfuramide. That's the one substance that truly is active. And these other formulations like the phosphinates and the phosphonates, that's where the materials are used or surfactants. They don't have an active role in the mechanism, but they provide they make it slippery and easy to move. But the sulfuramide is probably the most clearest example of a PFAS substance that's used and meant to be active.
Okay, great.
I don't know of too many others, actually, to be quite frank. That's the one.
It's the one that's left, I think, isn't it, Bob? That's the one that's still left.
Yeah, I don't know. I actually don't know of many, if any, others. With, of course, the caveat, as I mentioned earlier, for any of you taking medicines of just about any kind and folks using pesticides, there's fluorinated bits in those, but it's a different kind.
Right. Okay. We've got just under 5 minutes left, so hopefully we can get through a few more questions here. And we are certainly not going to get through all of them. I apologize, but so one question is, can you make production volumes available for the many different PFAS chemicals that you've talked about during your presentation?
I know, Bob, I cannot. I mean, I think companies, as you know, again, I think you know what my answer is going to be, Toffer, in the sense that companies don't share manufacturing production data. They don't share it, so there's no way to rack it up when it's. I mean, there are studies out there that from market research firms that try to guess at production, but I certainly don't know what current production is, Bob. I don't suspect you do either, because companies guard. And right or wrong, I'm not judgmental here, Toffer, that companies do guard what they make and what they use, as you can imagine.
Right. Okay, let's see. I'm trying to be selective here. So many questions to choose from. Again, it's still getting some questions. People are clearly interested in, questions around incineration. So one question is, are you aware of any studies of breakdown products or I guess it would be essentially products of incomplete combustion in sort of typical municipal incineration, rather than in optimal conditions? I think that's essentially acknowledging the fact that, municipal incinerators as they are currently run may not always perform at optimal under optimal conditions.
Yeah, that's a good question. So maybe circling back to the studies that we alluded to earlier that have been published, excuse me, looked at a progressively decreasing temperature range and saw mass balance of fluoride under those conditions. So at least to the extent that we're aware of, under the conditions explored, which some of them went well below even the minimum that folks are supposed to operate facilities, we saw mineralization.
Okay. Oh boy, there's still questions are coming in at a surprising clip here. So I think let's just try and get one more in, and I'm practically going to pick at random here. So PFAS have also been found in cosmetics and personal care products. And do you know, or could you talk briefly about what kinds of PFAS chemicals are used in personal care products and why, what their function would be?
That's a good question. I don't know specifically about a lot of the uses, but some of the polyether-based substances have been used in that area. That's not an area that I'm terribly familiar with. Some of them are registered within the frameworks for those kinds of products, and that might be a good way to ferret out and identify specifically what some of those are.
And Bob, I can, and again, I went to Dioxin in Vancouver a year and a half ago, whatever it was, and there was a talk or a poster talking about cosmetic uses, and believe it or not, and I was a little bit surprised given my background that folks were using in essence phosphate surfactants in cosmetics, which was incredibly surprising, I guess, as a wetting, leveling kind of action, but I don't know how prevalent that is still, but that was about a year and a half ago, and that folks were talking about, finding, getting things off the shelf and measuring, and that's what they found. And again, that was a year and a half ago. I don't know whether those chemistries and those uses still exist, but they did not that long ago, Taffer.
All right, that's great. So obviously we're out of time, and I first of all want to thank the two of you again for spending 2 hours with us and for the work you did to prepare. So thank you again. We do have a number of questions that we didn't get to. Would you be willing to, if maybe provide some answers, written answers to questions we didn't have time to get to that we could make available to the participants today?
Well, I certainly would be okay with helping as much as,
sure.
I don't have a problem with that at all.
Okay,
sure.
Great. Well, thank you.
You would compile them, share them, and then we'll talk about them, and we'll find a way to try to provide meaningful input to folks.
Excellent. Well, that's very much appreciated. And I know you want to give an additional plug or mention that you will be available in Boston at the ITRC annual meeting, as shown on your slide here.
Yep.
So, and again, I think if people have additional questions and are going to be attending that meeting, you've extended an invitation to speak with them then and there. Is that correct?
Absolutely. Absolutely. Yes.
Yes.
All right. Well, again, I want to thank you very much for taking the time to present to us, and thanks everybody for attending. Again, please, if you have a 2 or 3 extra minutes when you get the invitation to take the survey following the webinar, it would be great if you would do so. It helps us. We appreciate the feedback. So
we thank you, Taffer, for allowing us to do this today. Thank you.
You're very welcome. All right. Well, I think that basically brings this webinar to a conclusion. And again, I'll make the recording available on the IC2 website in the coming days. And I guess beyond that, have a great afternoon, everybody. Thank you so much.
Thank you.
Thank you.